Video we shall be discussing about a few problems related to the introductory ideas that we discussed on classical mechanics. Then we'll be moving over to the higher physics or the general part of the classical mechanics after trying these few problems. Now to begin with, we have a few easy ones which you already know. They are related to the connected motion. They will be like child's play for you if you have observed the videos that I've made on connected motion. Uh, this first one over here shows a compartment of well, the boxes or compartments of a train, and each has a mass m, and the engine applies a net force such that it drags those masses along its direction. You can see the direction of the force right there at the top. What we wish to obtain is the force that each of those box experiences. Now the forces that we can consider, well, if we I have marked those boxes 1, 2 and 3 as you can see in the figure, and in those boxes, the first one that is being dragged by an inextensible string. Now because the strings are inextensible and they are massless, which is usually the case in these kind of problems, until and unless they have been mentioned, you can consider them as inextensible and massless. And the tension that acts, because they're inextensible, so the tensions cancel out along that string. So T1 is equal to T1 primed, that is acting along the opposite sense, as you can see in that very first string that you have right here. And then as far as the acceleration of the entire system is concerned, the entire system being connected, the total mass has to be considered, so 3m, and the acceleration of each of those boxes will be the same. Now with acceleration being the same, the tension that is dragging the first mass, remember the case of free body diagrams that I had discussed in one of my videos, and there you have T1 to be acting along the direction of acceleration, which results in the force. So T1 is equal to m times of A as we have it is F over 3m, and therefore you have the tension or the force to be acting on that first mass as F over 3. Similarly will be the force over the second mass, the net force, but the force that is dragging it is obviously the sum of these two, that is T1 primed acting in the opposite direction and T2. So T2 from that is going to give us 2F over 3, and finally 3F over 3, or completely F, to be acting on the third mass, which is right near the engine. So you can have a glance at this and you can try it out yourself, and provided you have considered watching the connected motion video. Now the same goes with the case of the Atwood machine, the popular one, where the inextensible string goes over a pulley which is fixed, and it drags, or it has two masses. We need to obtain the acceleration as well as the tension along the string. Inextensible string, a single string connecting the two masses, the tensions will be acting towards the pulley, and the equations, supposedly m2 is greater than m1, so m2g will be dragging the system downward, while m1g, that is the mass, or the m1 mass, that will be dragged upward with the same acceleration, and therefore we have t minus m1g as the first equation and m2g minus t, and all of that is equal to the respective mass times of the acceleration following Newton's second law, and therefore we can calculate the acceleration as well as the tension. Now let's move over to the third one. In the third case, what we have is an expression for force in terms of the variables, the coordinates, that is x, y and z, and we have to show that the force is conservative if it is having this kind of an expression, and also we have to calculate the amount of work that is done by this force in moving the particle from a single point, that is 0, 1, 2, through to another point 5, 2, and 7. Now, the conservative nature of force, if you remember, we had discussed about this in case of while trying the theoretical part of the introductory ideas, that the curl of a vector is equal to 0, or the curl of f in this case being 0, results in that force being a conservative one. So that is exactly the case. We have the curl of f, and the curl of f is simply the cross product over there that you can see, and that del operator that you have is del over del x, that is the partial derivative with respect to x, y, and z, I cap, j cap, k cap, and you have the corresponding components of I, j, and k unit vectors for the force down there, that is that is 2x y plus z square, x square, and finally 2xz. And now you take the curl of that and you obtain it, and that goes to 0. So if that is 0, the force is conservative. Now, as for the work done, we'll do it in an efficient way instead of going the usual way, that is from the for the x, y, and z coordinates separately. We will first look at this, that we have this one as f dot dr. The dr carries dx, dy, and dz terms, so that's fairly straightforward. And the I components, j components, and the k components multiply, or we do the dot product over there, and we get these two terms that we have over here. Now these two terms, if you observe them closely, they are simply exact differential terms of these two, that is d of x squared y, the first one, and the second one is d of z squared x. And the integration stays as such. What we do is we simply set those limits, because x, the lower limit of x is 0, so we just put 5 squared over there. And as far as y is concerned, we have 2 minus we have 2, the value of y that is there, and then again we have the value, the higher value of z as 7, and then all of that is equated out to give us 295 joules, which is now this is very easy, because we need not consider about the lower cases, because the exact differential will lead us to the final result. So we have the upper coordinates that we had over there, and we put those values to get this result. Moving over to the fourth bit, we have two objects of masses m1 and m2, 200 and 500 grams, moving with velocities as given respectively, v1 and that's probably v2 not written over there, and just prior to collision, during which they become permanently attached to one another. And as a result of that, we have to calculate the velocity of the center of mass, the final momentum of the system in the laboratory frame, the initial and the final momenta in the center of mass frame, and the fraction of the total kinetic energy, which was the initial kinetic energy, of course. We have to obtain that is associated with the motion after collision. Obviously, the loss in energy would give us that. Now, as far as the velocity of the center of mass is concerned, we obtain the position of the center of mass first of all, and then we just do the time derivative of that position vector, and we get the velocity of the center of mass as over here. And then what we need to find is the final momentum of the system in the laboratory frame. The laboratory frame is the usual frame that we observe from, and in that case, the masses, after having, because of this the final momentum, and the masses have got stuck together, so the total mass will be this, and the velocity will be that of the center of mass that we have calculated out, and that results in this value, that is 3.5 I hat plus 2.5 j hat kilograms meter per second. As far as the initial and final momenta of the system in the center of mass frame is concerned, Well, the momentum in the center of mass frame is always going to be zero, as we have studied in the theoretical part of this series. That is also known as the zero momentum frame. That is the center of mass frame, and that is why the center of mass in the center of mass frame, the initial and final momenta are going to be zero. Then, as far as the kinetic energy is concerned, the total kinetic energy or the kinetic energy uh, of the particles prior to collision was this, that is half times of m times of their initial velocities squared, and that leads us to 18.5 joules. And what happens as far as the conservation of linear momentum is concerned is that we have the final velocity of the system to be this, which is of course the velocity of the center of mass. uh, that is what we have obtained, and with that velocity multiplied to the final mass, that is the mass after they have stuck together, so that is 0.7 kgs, 200 plus 500 grams, so we get the value to be this. Now the ratio or the fraction of the initial kinetic energy that has been used up is going to be this, that is the ratio of the final kinetic energy term over the initial kinetic energy term. So that's the entire question for you. I'm moving pretty fast, I know that, but you can always pause the video and look for the solution. Everything's been written, and in case you find any problem in understanding a few things, you can always comment below or approach me directly if you have my contact number. And then in the next question, we have the differential equation of a simple harmonic oscillator of mass m to be given as this, that is m times of d squared x over dt squared, and that is the second order derivative of x with respect to t, plus cxc being the force constant. And we need to solve the equation to find the expressions for the displacement, velocity, and acceleration. We are slowly moving over to the through the entire portions in mechanics, and then we'll be moving over to the higher portions in the later problems, as you will see. Now the differential equation as has been provided to us, x double dot is simply the second order derivative that has been mentioned over here, and we know that the double derivative is going to give us the acceleration, so that's the acceleration for you which was to be obtained. Now if we multiply a factor 2x dot, that is 2 times of the first order derivative of x, to the above equation over here, then we get this, and once we get that, that is an exact differential equation if you see, and integrating that, the right hand side 0 will give us an arbitrary constant, and so we are left with this equation. Now x dot, as you know, at the extreme points is going to be 0, because the pendulum swinging, or the harmonic oscillator in this case, swinging or moving to the extreme points, it pauses over there, the velocity goes to 0, that is why it cannot go any further, and that amplitude, as has been mentioned, is a. So with that amplitude, we have omega squared instead of the x square that we have over here in that expression. We'll be having a squared, and x dot is obviously 0, so omega squared a squared is equal to a, and we put that value over there for a on the right hand side of this expression that we had, and so we have x dot squared to be equal to omega squared times of a squared minus x squared, all under root, and this is nothing but the velocity. And finally, we also know that the velocity is the first order derivative with respect to time, first order derivative of the distance with respect to time, so dx over dt is what we have obtained. We can just cross multiply and integrate it. We get another arbitrary constant as a phi over here, but that's not a big deal. we have sine inverse function over there, so that goes to the other side. So we have the generalized expression the uh, for the simple, or the solution for the simple harmonic oscillator, the displacement formula, that is x is equal to a sine, and that's what harmonic is all about. The harmonic functions are the trigonometric functions that we deal with, and that is exactly what we have obtained. In the next bit we have a pulley once again, but this time we also have the disc, or the disc of the pulley, to be taken into consideration. Now we consider a system of two masses m1 and m2 and a pulley which also has a mass. Now in the previous case we had considered a massless pulley, so we are advancing into something else. So now we have the tensions along the string to be different, and as a result of those tensions there will be a torque acting on that pulley. And because the pulley has a mass and it has a moment of inertia I, the moment of inertia of the disc of the pulley is obviously about that axis about which it is rotating, is mr squared over 2 times of the angular acceleration, that is alpha. And the equations concerning, now we have taken or it has been given that we have m2 to be greater than m1. So in that case we have this m2g minus t2 and t1 minus m1g, all accelerating with the same rate, of course, and equating them we get this, we just add them up. So we get this equation number 1, let's call it equation number 1. And as far as the torque equation right at the top was concerned, we have alpha to be equal to a over r, that is the radius of the pulley, and the r terms cancel out and we are left with this, that is t2 minus t1 is equal to, well, t2 minus t1 is obviously the difference in the tension, and that is providing the necessary torque to the system. Remember, torque is also defined as the force acting tangentially uh, along that pulley, and also multiplied to the perpendicular distance from the axis, the point of action of the force, that is over here or over here, and obviously we are considering the difference of that, and the perpendicular distance from the axis of rotation, and that in this case is the radius itself, that is equal to r. And that is why we have that equation number 2. Now from 1 and 2 we can solve them and we get the acceleration to be this, and if we put those values of acceleration we can obtain the tensions that are developed along the string. You can try them yourself and look for the results and see if whatever I have obtained is correct or not, and in case they are incorrect you can always let me know. I am open for any kind of rectification necessary. Now the next bit has the position vector of a particle of mass m moving in the xy plane to be given by r vector is equal to a cosine omega t I cap and b plus b sine omega t j hat. A is greater than b. In this case we have to show that the path of the particle in this case is an ellipse, which is given by this equation right over there. And further we have to show that the force acting on the particle is always directed towards the center or origin in this case, and that has a magnitude of m omega squared r, and that force is also conservative. Now find the expression for the potential and kinetic energies of the particle in that above problem and show that the total energy is given by this, which remains constant, of course. Well, all of that we'll try it right away. So as you can see we already have the solution with us. I've already done that to save time. So we have r to be given like that because it's given in the xy plane, so we have the i hat component as x and the j hat component as y, and we can substitute those values, and from that what we get is x squared over a squared is cosine squared omega t, y squared over b squared is sine squared omega t, and we add them up. The right hand sides add up to 1 while the left hand sides are as per requirement in this equation, x squared over a squared plus y squared over b squared. Now force, as we know, is m times of the rate of change of the double rate of change of position with respect to time. So if we do the double derivative of that r that we have, then we'll be getting minus m omega squared r. Well, there was a mass, of course. Omega squared was obtained after we did the double derivative, and obviously cosine and sine, once you do the double derivative of the sum of them, you will be obtaining a negative in common. You can try that. It's pretty easy, so I haven't really gone through the process of calculating it. And what we were to show is that it acts towards the origin. Well, the negative sign that we have obtained, that just helps our cause in explaining the direction, which is directed towards the origin, of course, in the xy plane. And as far as the conservative nature of the force is concerned, well, we can just do the curl of the force vector, and as you know, curl of r is always going to be 0, so that is why we have obtained the result to be a conservative force. As far as the conservative force is concerned, the negative gradient of potential energy is equal to that conservative force, which is in this case equal to minus m omega squared r, which we have just obtained. We integrate that term, that is d over dr times of u, or d over dr of u, and that is equal to m omega squared r. The negative signs cancel out, and we find u to be equal to, well, after integration it's going to be obviously from 0 to r, it's going to give us this. And if we just open up that r squared that we have just obtained, then we have a squared cosine squared plus b squared sine squared term in the brackets. As far as the kinetic energy is concerned, we take the first derivative of r and we square it up to obtain the kinetic energy term. That is what I have done, and we have obtained therefore the kinetic and the potential energy term as was required. And once we have obtained them, we can just add them up, and if we add them up, we obtain all constant terms. There is no variable term in that, because the only thing that was varying with respect to anything was the time, or the factor omega t multiplied. Omega, remember, is the angular speed, and that's constant. And in this case, omega t was varying because t was the factor that was multiplied to it. With the absence of t in this expression for the total energy remains constant, and that is what we had to prove in the final part of the question. In the next case, we have the question number 8 on your screen. A particle moves under a force that has been given as a negative of k over r squared r hat as a unit vector. We have to prove that the angular momentum of the particle is conserved, and also we have to find out the nature of the forces, whether they are conservative or not, in those 4 expressions for forces that we have. Now I haven't really done these the second bit, that is the bit B. I have left it for you. What I can give you as a hint, I have the answers ready in my rough work. So all these 3, the curl of all of these 3 are going to be equal to 0, and hence the first 3 terms are going to give you conservative force, while the curl of this last term won't be equal to 0. You can check for yourself. I have provided you with the answer. You can check for yourself. As far as the bit A is concerned, well, I have done that explicitly over here. That is, r cross F is going to give me the torque, and F, as you know, is the rate of change of momentum, that is the force. This is Newton's second law, and r cross F is going to be the cross product of these two. you have a r hat over here, unit vector, and an r vector. Now r cross r is definitely going to give us 0. So the left hand side, as you can see, is 0, while the right hand side, the r goes or the r cross p is taken within that derivative, and r cross p is definitely giving us the angular momentum. Now the rate of change of angular momentum being equal to 0, the angular momentum remains constant or is conserved. As per the question, we had to prove that, and we have proved that quite efficiently. Now the ninth one has an expression for a potential energy. Now this expression that you see over there is the Yukawa potential. It's in nuclear physics. It's the potential inside the nucleus, and that is why you have the radius in that case to be of the Fermi units, that is 10 to the power minus 15 meters, and the potential term, that is the absolute potential term, or the rather the boundary potential term, to be equal to 50 mega electron volt. Now what we have to show is that we have to calculate, in the first case we have to calculate the corresponding expression for the force of attraction. Now obviously force of attraction, this is a conservative force, and we can take the negative gradient of the potential energy term and we get this, and as you can see in that expression we have a negative sign which tells us that the force is an attractive one. And then we are going to show the short range nature of the force just by obtaining the value of the forces in a distance at a distance away from that short range effective short range region, that is 4 times of that, and then at r is equal to r naught as well. As you can see, I have already obtained that with my calculation. I have this expression, so instead of r we have to put 4r at the top, 4r naught, and instead of r naught we obviously have r naught over here. So we put the value of r naught in this case for the denominator term, and over here as well, right, and over here as well. So we have those 3 r values where we are to put 4 r naught while considering the numerator case, and the denominator we have to put just r naught, and that's going to give us this value. Exponential, as you know, is 2.71. If you do not remember the value, I will just write it for you. E has the value of 2.71. that raised to the power minus 3 is going down in that denominator, and that's going to get multiplied. This value that we see over here, that is 0.0078, and that's approximately 1 over 126. As you can see, that it would have been 1 over 125 had that been 008, but it's 0078, and that is why it's 1 over 126. So that goes to show that how drastically the nuclear force decreases with the increase in the distance. So that tells us about the short range nature of the nuclear force. In the next bit we have another case of a nucleus which was initially at rest, but this is more mechanics based. A nucleus initially at rest, it decays radioactively by emitting an electron of a certain momentum which has been given 1.73. The unit here is a mega electron volt per c. C, as you know, is the speed of light, and perpendicular to its direction we have to the direction of the electron emission we have a neutrino which has a momentum of 1 mega electron volt per c. In what direction does the nucleus recoil? Well, this nucleus is the nucleus that is residual, the residue that we have, so that recoils while the other particles fly off. And what is its momentum in that unit that we see, that is mega electron volt per c, and also in SI units. Now if the mass of the residual nucleus is 3.9 times of 10 raised to the power minus 25 kgs, then calculate the kinetic energy in joules as well as in electron volts. Okay, So to begin with, the initial momentum of the system was obviously zero because it was at rest. And then we have this the momentum of the residual nucleus over here, the momentum of the electron over here, and the momentum of the neutrino. The sum of all of that is obviously going to be zero because initial and final momentum are the same as per the conservation of linear momentum. From that, what we get to know is that Pn, that is the momentum of the residual nucleus, that is equal to the resultant but oppositely directed to the resultant. It's more like the equilibrium of that of those two vectors. So magnitude wise, what we see over here is uh, Pe squared plus P nu squared, and remember the angle between them that was provided was 90 degrees because the neutrino flew off perpendicular to that of the electron. So from that what we get is that the cos 90 term that we would have had, that is obviously going to zero, and so we have the sum of them. Now 1.73 can be taken as root 3, so root 3 squared and 1 squared, so that adds up to 4, and all under root gives us 2 mega electron volt per C. And if we put that value of electron volt, that is 1.6 times of 10 raised to the power minus 19 joules, and we have 2 mega, which is 2 times of 10 raised to the power 6, divided by C, that is the velocity of light, so that is 3 times of 10 raised to the power 8. We get this value in kg meters per second. This was in mega electron volt per C over here, and this is in kg meters per second as per the question. Now as far as the direction is concerned, because this is a vector quantity, we need the direction over here. So I have tried to explain that to you diagrammatically. So here we have the electron, and 90 degrees to that we have the neutrino, and the resultant of them supposedly is in that direction, making an angle phi with the electron. And we have opposite to that resultant, that is from this equation that we saw over here, opposite to that direction of the resultant, we have the recoiling of the residual nucleus. Now all we need to do is we need to find this direction of that resultant over there. Now because we know from our vectors portion that tan phi, that is the angle made by the resultant to the electron in this case, so the electron stays alone, that is the momentum stays alone, and the angle between the electron and the neutrino is 90 degrees. So all of that done and dusted, we get 1 over root 3. Now tangent of something is equal to 1 over root 3, means that something is 30 degrees. So the resultant makes an angle of 30 degrees. Now resultant making an angle of 30 degrees, 180 degrees to that is this residual nucleus. So the residual nucleus is definitely going to make an angle of 210 with respect to the electron, or probably in this case we can say it's going to make an angle of 150 degrees with respect to the, not 150, 120 degrees with respect to the neutrino. 120 plus 90, that's 210 as well. Well, having obtained that, we can now obtain the kinetic energy of the residual nucleus with the mass. Because we have the momentum, we just take the square of the momentum and divide it over by 2m. The mass has been provided, 3.9 times of 10 raised to the power minus 25. I would rather suggest you to do this cleverly, and that is exactly what I have tried to show you while calculating these stuff. Now instead of using this uh, pathetic number that we obtained, we can just use these values. The square terms will have a 2 squared over here. This is 1, this is 2, 2 squared. 1.6, well, that can be taken as 16 times of 10 raised to the power minus 20. So 16 and 16 over here. Down below we have 3, so 3 squared is 3 and 3, and then that is further divided by 2 and 3.9. 3.9 can nearly be taken as 4, so there's no problem with that. You calculate all of that, and that's pretty effective calculating them this way instead of using that boring number of 1.066. So in this case you have a greater chance of cancelling out the bigger numbers. So this is what I've obtained in joules, and in electron volts you simply have to divide it with that figure, that is 1.6 times of 10 raised to the power minus 19, and that is the 10th bit that we discussed right away. We have probably 10 more questions to go in this video. We'll try to make it fast. Let's see. Well, the 11th one, we have an alpha particle which is emitted from a uranium nucleus, that is U-238, in radioactive decay, and the speed and the kinetic energy of the alpha particle has been provided. That's over here, here and here. That's the speed, that's the energy, and we need to calculate the recoil speed and the kinetic energy of the residual nucleus. And now again, conservation of linear momentum, initially 0, finally you have the alpha particle as well as the residual nucleus, and from that you have the velocity of the nucleus. And the velocity of the nucleus, because you have a 4 factor, that is alpha particle, going away from it, all that is left is from 238.4 going out is 234 that remains, and the result is this much, that is the recoil speed that was asked was 2.4 times of 10 raised to the power 5. And then in order to obtain the corresponding kinetic energy of that term, we just take it as p squared over 2m. Now again, I would try to do it in a more effective way. Now, because as we can see over here, the magnitude from this, the magnitude of the momentum of the alpha particle is going to be the same as that of the residual nucleus. So instead of taking Pn squared, I used P alpha squared, which is already given. So instead, from this velocity I would have had to calculate the momentum and all of that, but that was not necessary. I took P alpha squared, and that is over 2mn. That is the mass of the residual nucleus, of course, that is to be taken. But what I did was I multiplied the mass of alpha particle over here, the mass of alpha particle over here, which allows me to use the kinetic energy of the alpha particle, because now I have P alpha squared over here, m alpha, and the factor 2. So that is kinetic energy of the alpha particle. And that what else is left out? Well, the things that are left out is m alpha and mn. I use those values, m alpha and mn, and the known value of 4.212 in mega electron volt units, and the result was pretty easy to obtain. So you can try in your own short methods. This one was a shortcut for me. I hope it is helpful. Now in the 12th one, we have a stationary body of mass m, of mass 3 kg, not m, and that explodes. That explodes to 3 equal pieces. That means 1 kg each. And 2 of those pieces fly off at right angles to each other, that is at 2 I hat meters per second square, and then we have 3 j hat meters per second square. So the velocities of those 2 right angle particles have been provided, and the explosion takes roughly 10 to the power minus or 10 microseconds to be precise. And then we have to calculate the average force that is acting on each of those particles. Now again, conservation of momentum. Initially momentum was 0. Finally we have the sum of all the individual momentum. So each mass is 1 kg, 1 kg, 1 kg. We have 2 I cap, 3 j cap, and this one is unknown, so we calculate the velocity of the third particle over there, and the average force is simply the change in momentum over the time. The time interval, as you can see, is 10 raised to the power minus 5 seconds, and the initial momentum of each of those particles was 0. So the change in momentum, 2 I cap let's say for the first body 2 I cap, which was moving at I cap speed, 2 I cap minus 0 over that value 10 raised to the power minus 5, so that's giving me this much in Newton, and I cap is its direction. And the other one is going to be, obviously, as you can predict now, is 3 times of 10 to the power 5, considering the change in velocity being equal to the initial one, or the change in momentum being the initial one. Momentum here is velocity because the mass is 1 simply, and the force, the third particle, you can always calculate, so that's the average force in each of those cases. I hope this was pretty straightforward, so I didn't really bother about calculating the third force. Now the next bit, the 13th one, we have a bomb. Goodness me, we have a bomb which during its flight it explodes into two fragments with when its velocity, now it was moving with velocity of course initially, so here the initial momentum won't be 0, but the smaller mass, which is a mass m, that flies off at this value that we have over there, and the velocity of the larger mass, well, the larger mass is 3m, that is 3 times the smaller mass. We need to calculate the velocity of that, and we also need to do it in the center of mass frame as well. Well, let's calculate the velocity first. The conservation of linear momentum, the initial momentum of the system, because the total mass is going to be 4m, 3m plus m, and with the initial velocity provided, we just need the velocity of the larger mass, and all of that equated out, we have the velocity to be this much in meters per second. Now in center of mass frame, the velocity of the center of mass, or the center of mass frame, is the zero momentum frame, and because it's the zero momentum frame, the velocities of the fragments, that is what I have written over here, the velocity of the fragments will be relative to the motion of the center of mass. Now the center of mass obviously moves with that velocity. It's actually PCM, not VCM, it's PCM. So the velocity of the center of mass is what it was moving with initially, and it continues to move like that, and the velocities thus obtained for each of those particles after that explosion is going to be relative. So for that small mass, if its velocity is this and the initial velocity of the entire system was this, so the relative velocity is going to be this, that is the difference in those velocities. Similarly is the case for the larger mass, that is 3m, and it's again the subtraction of the velocity of the initial velocity term. Now the 14th question that I have for you, the solution, I have actually done this problem, this numerical, in one of my videos on vectors, the vector numericals, the third on that playlist. I'll also be providing the link over here. I'll be fixing the cards, so you can click on that card, the I information button that you see, icon that you see at the top of this video right now. So there are 3 particles. Let me read the question for you in case you have already seen this, you will be familiar with the result. So the 3 particles are located at the 3 vertices of an equilateral triangle of length of side L, and there may be a different dimension given in that case, probably A or something, I don't remember exactly. Each of those particles start to move with a constant speed v, with the first particle heading continuously for the second, and the second heading for the third, and the third for the first. And when will the particles meet? Obviously the particles will meet, they will meet right at the center of that triangle, that is at the centroid point, and the link to that video, or the card to that video, has been provided at the top. You can refer to that, or you can just move to the vector numericals playlist and move over to the third video in that series. Now I've solved it actually in two ways, so you can use any of those ways that you find favorable for yourself. Now the next question, the 15th one, has two swimmers to be leaving a point P on one of the banks of the river, and they reach the point Q, which is lying right across the other bank, and one of them crosses the river along the straight line PQ, that is straight ahead, straight away, and while the other swims at right angles to the stream, means he starts off perpendicularly. Don't know where he will end because there will be a drift for sure. So, and he walks, he then, so he has to walk. He walks the distance he has been drifted through on the other side of the bank to reach the point Q. Now we have to show that the velocity of his walking such that both the swimmers reach the destination simultaneously is given by this clumsy expression that we see over there. Well, the u that has been given over there at the top is the stream velocity, and the v, capital V, is the velocity of each of those swimmer in with respect to water. Now with respect to water means not the stream, the water is still water, so that's the velocity of them in water. Now each of those swimmers, I have numbered them. So the first swimmer, let me say the swimmer 1 over here, he starts off like this straight away, like this, but he is drifted along this direction and he ends up at this Q prime point on the other side of the bank, starting from point P. While the other one, he started, in order to reach directly to this point, he started off at an angle alpha, and he was drifted along and he reached the point Q. Now this swimmer who was drifted to the point Q exactly right across, he will take a greater amount of time because he started off against the flow of the river, while the first person, the person swimmer 1, he will take less amount of time because he started off his velocity was added up by the stream. Well, to calculate those velocities, we have we can take the width of the river to be d, and supposedly the swimmer 1 was drifted through a distance x that I have shown in the figure over there. And from that, what we can calculate, because that's 90 degrees the direction of the swimmer as well as that with respect to that of the stream, so we have a cosine 90 term which goes to 0, and the distance that he has covered, or the distance that he has moved, is going to be d squared plus x squared, because d squared the width of the river as well as the x, that is the drift, and the time that he has taken is t1. So you have an expression 1 over here, equation 1. For the swimmer 2 who starts off at an angle alpha, well actually he is with the stream moving to the right of your screen, the stream is moving along this direction. So with the stream moving to the right of your screen, the person will make an angle alpha plus 90 degree with the stream, and as a result of that we'll have this to be the resultant. And obviously the distance here is the displacement is d exactly, because there is no other drift, even if he has drifted, but he has started off at P and reached exactly at the opposite point Q, and the displacement is going to be d, of course. So d over the time taken by him is t2. Now if we use that cosine alpha plus 90 is minus sine alpha, and sine alpha, as you can see from this triangle that we have, sine alpha is going to be u over v, that is the stream velocity over the velocity of the person, and we use that and we obtain the expression 2, that is the equation 2. Now from those two equations, that is 1 and 2, because we have the time t1 and t2 now, we can obtain the difference in time. The difference in time is del t, and with those expressions you can play with them a bit. I have done my rough work, so I have in order to save space as well as time, I have written that directly for you. You can write that directly, or else it'll be better if you calculate it yourself, and you will obtain, my guarantee, you will obtain this expression for sure. Then you have the value of del t, and you can see an x over here. That x is nothing but the distance that the person has drifted through, the swimmer one, and that distance that he has drifted through divided by the difference in time is exactly the velocity that he has to take in order to reach the other side. So from that, what we get is we get the velocity, that is x over del t. This is the velocity with which he must walk so that he reaches the spot Q exactly at the same time as that of the second swimmer, or the swimmer 2 that I have taken. And the expression for that is what we had to determine initially, which is what you can see at the top as well. So this requires a bit of calculation, and I have done my bit. I would rather ask you to try it yourself as well, because once you try them, you tend to memorize them a bit as well, and that's helpful from the exam point of view. In the next case, we have a prism of mass m, which is with an angle theta, and a block. It rests on a horizontal table, of course, and a small block of mass m is placed on top of it, and it slides down, obviously. We need to calculate the accelerations of the prism and the block. Now, because well, the surfaces that we all have in this picture, they are all frictionless. Now, as the block slides down, that is what I've written over there, so that you get a fair idea of what is happening. How is that bigger incline or the prism moving? Well, that's moving because owing to the conservation of momentum, because as the block slides down the prism, considering the conservation of momentum, a considerable impact of the mass m acts on the bigger mass m due to the absence of friction, of course. Had there been friction, probably things would have been different, but due to the absence of friction, obviously the mass m tends to move in the opposite direction, and therefore initially being at rest, it starts to move. Obviously it accelerates. Now, with the acceleration of the block, the component acting along the weight of the prism that you can see in that picture over there, you have an mg sine theta to be acting along this direction, that is downward direction, and then you have 90 minus theta, that's the angle over there, towards the, when we consider the downward direction. So mg sine theta times of cosine of 90 minus theta leads to this. Now this is the component of the mass, or rather the force, that is acting along the downward direction due to the motion of that block. Well, because mg would have been the weight of the block that would have acted in the downward direction, but we are not concerned about the stationary stuff that is happening. That won't really contribute to any kind of acceleration of the entire system, or rather I should say the bigger mass, that is m. So that is why we need not consider that. So we consider the force that is acting in the downward direction due to the motion of the block, and with that motion of the block taken into account, we also have that to be adding to the weight of the bigger block, that is the prism. So we have the total weight due to this as mg, which is the weight of the prism, as well as the mg sine squared theta component, and that weight contributes to this mass that we have over there, m plus m sine squared theta. Take the g out and you have the have an effective mass to be acting there, and that effective mass, well, that is being accelerated now, but in the opposite direction to that of the block, and that acceleration is obviously going to be mg sine theta cos theta. Why? Because mg sine theta is going to act in the downward direction. Obviously the block won't be going in the upward direction, but obviously the block would be moving along this direction, that is the acceleration of the mass m that I have shown, and that is due to, as a result, that is the result of this reaction force, that is mg sine theta, and the component that acts along this line. So exactly opposite to this is this acceleration. So am there is equal to the force, that is mg sine theta cos theta, divided by that effective mass that we have obtained due to that prism, as well as the motion of the block over that prism. Now, because the prism moves, the acceleration of the block is affected. The block, which was moving probably at g sine theta being the only acceleration, because of the motion of the prism or the acceleration of the prism in the opposite sense, we have a relative acceleration. The relative acceleration in this case is going to carry the cosine component of the acceleration of the bigger mass, that is the prism, because that's what we are getting over here in the picture. Am is acting in the backward direction, but am cosine theta is acting in the upward direction, and that is going to add up to the acceleration. That being a vector quantity, we will be having a relative acceleration. So all those terms added, you have the acceleration of the block to be equal to that expression that we have obtained over there down below. So that's the 16th one. We move over to the next one, that is the 17th question. We have 4 more, that is 17, 18, 19, 20. I would request you to be patient and try out these problems yourself. You can take your time, pause, and come back and save them, whatever you can do. I'll have to complete it in one go. So the 17th one is that of a small block which is starting to slide on an inclined plane that has been provided, which is inclined at an angle theta with respect to the horizontal. The friction coefficient depends on the distance in this case. So there is a friction and it depends on the distance, and the friction coefficient is dependent as alpha times of x, where alpha is a constant, x is the distance covered, and we have to find the distance that is covered by the block till it stops. Obviously, friction acting, it may stop. So we'll have to obtain that distance that it has covered before stopping. It was initially at rest, it was left from the top at rest, of course, but it gradually increased in its velocity. But with the friction acting, or friction directly proportional to the distance, the friction increases and gradually stops the block. And then we also have to find the maximum speed that it can achieve within this distance that it has covered. Well, the first point, its velocity was 0. The ending point, its velocity is going to be 0. In between somewhere, it's going to achieve a maximum velocity, and that is what exactly we have to find out. Well, as for the first part, we have the net acceleration of the system, that is g sine theta along the slope, minus mu times of g cosine theta, that's the mg cosine theta is the reaction force, and that is why you have mu times of reaction force being the frictional force, and that's school stuff, so need not elaborate that. But now we have a variation in that frictional force, that is alpha x. And the left side, as you can see, is dv over dt, the acceleration. We can write it like this, that is dv over dx and dx over dt, that we used to derive the equations of motion. And then we, on the right hand side, we have the term as they are. Now v dv, because dx over dt is going to be v, so this is v times of dv, and this dx over there, that went to the other side, and if we integrate that, we'll have v squared over 2, because the final velocity is 0, so somewhere between it will be achieving a speed v, and the final velocity is taken as 0. And then we have the other term over here, that is that has the integration of x. So the first term now has an x, and the second term x dx integrated gives x squared over 2. Now that thing that we have achieved, that is the velocity. Well, that is at the end that is going to be 0, isn't it? With the total distance covered, the final velocity is 0. So we put 0 for that v, and the right hand side term completely equal to 0. On the left hand side we have now the distance that it has covered till the end point. As far as the maximum velocity is concerned, we have this expression over here. The star mark is just to tell you that we need to consider dv over dx as 0 for the maximum velocity, because the velocity is here changing with respect to the distance owing to the negative force that is provided by the friction, or negative acceleration provided by the frictional force. And with that 0, so that left hand side of that term at the top just below the diagram, that goes to 0, and we are left with the right hand side term, and the right hand side term yields the value of x to be that much. We put that value of x in, so that's the condition for maximum now, and we put that value of x in the expression, that is this one that I have just circled. So in that expression, if you put the value of x that we have obtained over here, then we are going to get the maximum velocity corresponding to that motion, and that comes out to be something like this. You can try it yourself. You can pause the video, you can solve that for yourself, and you'll achieve this, I'm sure. In the next question, we have a bullet of mass m moving horizontally with a velocity v, and that passes through a pendulum bob of mass m, capital M, and emerges with a velocity half its initial, that is v over 2. If the length of the pendulum is L, calculate the minimum value of velocity with which the bullet was fired so that the pendulum bob will complete a circle. So now we have a condition for minimum velocity of an object moving in vertical circles, and that minimum value is root over of 5 times of g L. L here is the radius of that circular path, or the length of that string, take it as you like. So that's the minimum velocity that is required for the bob of that pendulum to complete the entire cycle. That's the case of vertical motion. We have I've provided tagged the video in this description as well. Not in the description, but as you can see at the top in that eye, you can click on that and you'll be reaching that video as well. So as far as the conservation of linear momentum is concerned, initially the bob was at rest, so no need to consider that mass. The velocity of the bullet times the mass of the bullet, mv, and then we have the bob times the velocity, minimum velocity, which we know is root over 5 gl, and then the velocity of the bullet after it has emerged out, multiplied to the mass of the bullet. So taking that into account, we obtain the velocity of the bullet that must be the case so that this bob of the pendulum that moves an entire circular path. So that's the 18th one. We are left with 2. So here are the last 2 bits that you can see on your screen. The first one being a small body of mass m has a horizontal velocity v naught, and at the point P, starting point probably, and then find the maximum instantaneous power that is developed by the frictional force if the coefficient of friction varies as was in the previous or prior to that case, that is mu is equal to alpha times of x. Mu is the coefficient of friction, alpha is a constant, x is the distance from the point O. That is what I have shown in the diagram there. So here's the mass, it was moving with the velocity, and now at a distance x we have to obtain the power, instantaneous power that is generated by the frictional force. Only the frictional force is concerned, so frictional force multiplied with velocity will give us the power term. The force in this case is mu times of mg. Mu is alpha x as you know it, and the negative sign obviously suggests that it's going to be decreasing. And as far as the velocity at that point is concerned, we can calculate the velocity from this expression that we have over here. That is, the acceleration is obviously the frictional force divided by the mass. The frictional force was over here, and we simply skipped the mass term and we have the acceleration now. And with that acceleration, we'll have a velocity, final velocity v minus v naught squared, and that is equal to this. So we put that value of v in this case, that is f times of v, so v is that. Now, as far as the maximum instantaneous power, the maximum power can be obtained by the condition of the first order derivative, and taking the first order derivative, we have the right hand side to look like this, and we then set that to 0. With setting that to 0, we obtain the value of x, and we put that value of x because it's distance dependent, so we put that value of x right up in that first equation, and what we get is this one, which yields the final expression to be this in terms of magnitude. We have done away with the negative sign, so here's only in the magnitude form. And you can calculate all these calculations. You can pause the video and you can try them yourself. They are pretty precise and clear. You can check for yourself. I would be happy if you try them yourself so that you can get the get to know the or practice yourself in a better way. Now the last one from this video, the 20th one, that has a smooth sphere of radius r, and that is made to translate. So this is translating in the forward direction with an acceleration a, and constant acceleration, of course. A particle is kept on top of the sphere and is released from that point at 0 velocities with respect to the sphere. Why do they even do that? Okay, now find the speed of the particle with respect to the sphere as a function of angle alpha with which it slides. Now here the particle supposedly was at the point O. The sphere is translating in the forward direction with an acceleration a as shown. Now as the particle slides down, it reaches supposedly a point A. It makes an angle theta, as you can see, with respect to the vertical or from its initial point, and correspondingly along that axis, along that vertical direction, the projection on its line with respect to the origin is taken O prime, while the initial position is taken as O. The position along that y-axis is a primed, the projection over there. So a lot of things have been marked, and the radius has been provided as well, that is r. So what we need to find is an expression for the velocity in terms of that angle. Now we can use the conservation of energy, or probably the work energy theorem, to our effect. Now the total work done in this case is mgh along the vertical line, and ma, that is the force that is acting in the forward direction, times of the displacement in the forward direction. Displacement in the forward direction from its initial point is obviously a primed, and OA primed is the height that it has come down. So, and that would lead to the change in kinetic energy, isn't it? As per the work energy theorem, we have the change in kinetic energy. Now the initial kinetic energy is obviously 0 because the particle was left at 0 velocity with respect to the sphere. Remember, that was provided in the question itself. So the change in kinetic energy will be equal to the final kinetic energy only. And as far as the work is concerned, we have two of those cases, and this was pretty simple considering that we didn't have to use any vector quantity. We just used up the energy terms and we obtained the result. So we have the final velocity as this. Now to end the video with this question actually was to tell you that we will be simplifying our problems, and we'll be getting rid of those vector terms that we have been studying day in and day out. In the upcoming videos, we'll be learning them how to get rid of those vectors for complex situations and to make things easier just by considering the energy terms like we did in that last question. So that's all from this video, and for the upcoming videos on the theoretical as well as the numerical ones, stay tuned for that. Till next time, thank you for watching.